So, good morning, everyone. Good to be. So I continue on this talk on Multilevel Monte Carlo, but before that I also had a little announcement. So for your information, we are organizing a summer school. This summer, actually, I'm not really organizing, but more all my PhD students together with Tommaso here in the room, and Zenga was former postdoc in the room. So this will be at in June. The topics are a little bit small there, but not four topics on the second announcement, there is a postdoc position available at the EPFL, if anyone of you might need. Okay. The plan for today, let's see if I managed to cover the whole list. So yesterday I went up to this point. I never read that. So I covered the basic multi-level Monte Carlo estimator and the complexity analysis. So essentially, the method that was developed by, popularized by Mike Giles with this complexity analysis and implementation aspect and application. Today, in the first hour, I would like to discuss some variants and generalizations, in particular the unbiased version, unbiased multi-level Monte Carlo, which is a nice twist that could be used in some cases. The multi-indexed Monte Carlo, it's a generalization of the multi-level Monte Carlo. And I would like to say a few words on the Multifidelity Monte Carlo. Again, there is a sort of zoo, there are many versions of this. I would like to discuss the version that was proposed by Benjamin Hausdorff and Karen Wilcox and Max Günzburger a few years back, and how somehow it relates to multi-level Monte Carlo. So probably this I will do after the coffee break. And then at the end I decided to present a couple of less obvious or more advanced applications of multi-level Monte Carlo in the context of data assimilation. So we discuss one multi-level version of the ensemble-Kalman filter that we have developed, I think, also a few years back, and a multi-level MCMC for Bayesian inversion that is essentially the method that Rob has proposed, Rob Scheichel with Arita Tekentroop and a few other, and we have somehow slightly generalized and did some analysis of that method. I'm not sure I will get up to that point, so let's see how far it can go. Just for those of you who were not here yesterday, I recall the notation that I will use throughout. So I have, suppose I have some random equation, parametric, or so with a random coefficient. So U is a solution and Y is the randomness in the system, and we are after some quantity of interest, so some output Q, which is a Q tilde of U, so some output computed from the solution of the differential model. So for any validation of the random variable, you will get some output. This output could be a scalar, a vector, or more generally a function in some function space Z. And I hope I convinced you yesterday that you can do easily the whole analysis if you're in a Hilbert setting, the bound is a little bit more involved. Okay, so that was for just to recall the basic answer. One more. And of course, the differential model is complex, so usually we don't have the exact access to the exact solution of the differential model, so we need some computational model, which I denote with an H. It could be a finite element discretization of your PDE or some time integrator for an ODE or an SDE. And then this discretization implies an approximation of the output quantity, which hopefully will converge at a certain rate to the true quantity of interest. So we assume that we have some convergence at least in some piece moment with p at least equal to 2. Okay, so let's now go to the today's part. So first variant or generalization of the multi-level construction is this nice idea of an unbiased multi-level estimator, which was proposed by Lee and Lin in 2015. And this is how, I have discussed yesterday the standard multi-level Monte Carlo, and I said that multi-level Monte Carlo is a biased estimator of the true quantity, because at the end we have computing the expectation on the finest grid, and then we have this bias variance decomposition, and then we can split the tolerance among the bias and the variance, so we have to find the finest discretization level to control the bias, and the sample sizes to control the variance, and then we can do the whole analysis. So this is an unbiased version. So it means that really you target the true expected value mu. So how can you get rid of the discretization error, in quotes? Of course you don't. That's the aim. So here is how it works. So again, suppose that you have a sequence of discretizations, but now I consider an infinite sequence, so I want to up to convergence. Okay. And I assume that this discretization induces a discretization of the output Q, which converges in L2 sense to the true output Q. So in L2 with values in this, let's say, Hilbert space Z. Okay? So if you have this convergence, then you have that, again, this expected value of Q, you can write it as a telescopic sum, but now it's an infinite series from 0 to infinity. So I don't stop at capital L, at the finest discretization level. Virtually I go to infinity. Okay? So this is an equality. And now the trick is here. So okay, let's interpret this infinite sum as an expectation over the integers. But of course, like this it doesn't work because it would have a unit mass on each integer, so it's an infinite measure. So I have to scale each term. So I apply the 1 over, so I choose a probability mass function over the integers. So a sequence of positive, non-negative p's that sum up to 1. I rescale each one of these differences by ql minus ql minus 1 as 1 over pl. Okay? And then, I reinterpret this infinite sum as an expectation over a random variable, integer valued random variable L, that is distributed according to that probability mass function of 1 over PL times this difference QL minus QL minus 1. So this integer valued random variable is distributed according to this probability mass function. The Y random variable, the underlying noise, has its own distribution rho, and those two random variables are independent. Okay? So I hope it's quite obvious that what I wrote is correct. So this expectation over L and Y, because of those two random variables are independent, I can, so it's a double integral if you wish. To be, I can write it as an expectation over L over expectation over Y. Okay. 1 over PL QL minus QL minus 1. Now this expectation over L, I spell out exactly what it is. So it's a sum over all possible values that the random variable L can take of this inner expectation. times the probability that L takes the value J, which is exactly the, sorry, this is J, the index. Times the probability that L is equal to J, but this is exactly Pj, so this cancels this Pj, and here you get the expectation of Qj minus 1, which was his original infinite sum. Okay? So just a trick to interpret this infinite sum as an expectation over the integer valued random variable. And once I get to this point, well, the idea now is to do a simple Monte Carlo estimator on this expectation now. What does it mean? It means that now I have to draw many times y and L independently. Okay? So I draw m times these differences on a random level. Okay? Where the random level is taken from this discrete measure. Okay, so here is the estimator. Again, you have to teach for each sample, you have to draw a level, you have to draw a realization of the noise, you compute this difference, and you take the average. And it's unbiased because if I take the expectation of this, I get to this, which is equal to that, which is equal to mu. Okay? That's the trick. So ideally, if you keep on sampling, of course, this probability mass function with decay has to sum up to 1, so the probability of getting very high levels becomes smaller and smaller. But if you keep on sampling, eventually you will explore all the levels. Eventually, you will converge to the true value. Okay? So a little bit of theory of this version. Does it work in practice? So this notation I call delta J as yesterday, this difference Qj minus 1. And in the theory, what appears is the variance of this difference. The variance taken at a fixed J. So I call this B tilde J. Maybe yesterday I just called it Bj. Yeah, probably change of notation. This is B tilde J, so it's the expectation with respect to Y of this delta J, measured in the right norm, square. Yes, sorry, I'm not, so this, I put a tilde because this is not the variance, it's just the expectation of the difference square. But not subtracting the mean. That's the detail. Okay, so the variance, so let's look at the variance of this new estimator. So the estimator is unbiased, so the mean square error is just the variance. So the variance of this estimator, again, this is a standard pure Monte Carlo estimator, okay? So with independent realization, so the variance of the estimator is just the variance of the quantity itself, delta L over PL, divided by the sample size, okay? And the variance of this random variable, so where L is a random variable itself now, okay? So the variance of this random variable here, I can write it as the second moment, the uncentered second moment, minus the mean squared. Now, if you're sloppy, you could just throw away this term in upper bound just by the second moment. If you want to be more careful, as they were in the paper by Rin and Glynn, you keep it. So let's spell a little bit more. So now this expectation is again a double expectation with respect to L and with respect to Y. Let's spell out exactly what is the expectation with respect to L. Is this infinite sum. 1 over, so I have 1 over Pj squared from here, but then I have to multiply by the probability of L taking value J, so 1 Pj disappears, so I get only 1 over Pj, expectation over Y of this delta J squared, okay? Which is the tilde that I have defined here. So the variance takes this form here, this relatively simple form here. It looks similar to the variance of the multilevel Monte Carlo, okay, except for this minus mu square, because I'm using uncentered moments. And in a sense, you see that you have so the multilevel Monte Carlo, so the variance of the multilevel Monte Carlo, the one I discussed yesterday, was the sum of all the levels of the DL. Now this was the true variance, not the second moment, but let's forget about this difference, divided by ML. And here, if I forget the mu square, I get so the variance of this uncentered, unbiased multilevel Monte Carlo with the infinite sum, this time, of the second moment divided by m times PL minus this mu square. So essentially, this m times PL plays the role of ML. So I draw m samples, I have a budget m, but then the probability of ending up in level L is essentially m times PL. So the number, on expectation, the number of simulations that I run on level L is the equivalent of the ML that I'm using. Okay, so now if we want to optimize this estimator, we have to find a good choice of PL. So now what we have to tune, we have to decide the overall sample size to achieve a certain tolerance, but we have also to choose this probability at which we sample from the different levels. How do we do it? Well, again, we try to optimize the method. We can, yesterday I discussed the optimization where you minimize the cost for a given error, so for the given variance. Here I do the opposite, but it's the same, so I fix an expected cost. So notice that the cost of this estimator now is random because you don't know at which level you run the simulations. But the expected cost will be, again, each simulation has a cost, a random cost CL, depending on which level you picked. And you run M simulations, so the cost is the expected cost is the expectation of M times CL. So if I fix the budget, so if I fix the expected cost, now I want to minimize the variance, okay, over M and this probability mass function, okay. So P, of course, are constrained because they have to be non-negative and sum up to 1. Okay, so this is how I run the optimization. Now, from here, I can just get directly what M should be if I want to meet the budget. So M should just be taken as the overall budget divided by the expected cost. And the expected cost, again, is this infinite sum of the unit cost. Sorry, there is a typo, it should be J. That's the unit cost on level J times the probability of drawing the level J. Okay? So now if I plug this M here, what I have to minimize for the probability is this product, this variance times this inverse, this expected cost, okay, over P, linear probability mass function. Okay, now you can work out the calculations. I have the proof in the next slide, but you do get an explicit, slightly less explicit than for the MLMC, in the sense that you have to solve a nonlinear equation, but it is still doable. So Pj is essentially proportional to V tilde, square root of V tilde j over Cj, so it's similar to Monte Carlo, but there is this extra mu square at the denominator, and this constant k star that you should find so that this is a proper probability mass function, so it's sum up to 1. It means that you have to solve this equation here to find the right value k star. So if you forget about the mu square, we would get essentially the same formula as for Multilevel Monte Carlo. But if you keep them in square, okay, it's slightly more complex and you have to solve that equation. Equation which, by the way, has always a solution. You can show because it is decreasing in k star. So if you let k star go to infinity, this j, this whole sum go to 0. If you evaluate a j in 0, you just get square root of v square divided by mu square. And v square is a second moment. So you can lower bound it by mu square. So you get 1. You get something that is surely larger or equal than 1. Okay, so you start above 1 and you go to 0, so there is a solution. So now we have a formula for the optimal probability. So I can plug it in the variance here, and I get a formula for the minimal variance that I can achieve with this method. So it's this constant k star divided over the budget times this sum of Cj, Pj, optimal Pj square. Yeah, that's the formula for the raw variance. Okay, here is the proof. I can leave it as an exercise. So just write a Lagrangian, you take a derivative with respect to each Pj, and then you have to solve this equation and figure out what the Lagrange multiplier is, and you can do some steps, and you get to the formula. Okay, so how does it perform in terms of asymptotic complexity? So let's compare it with the standard multi-level Monte Carlo. By the way, there was an assumption in the previous result that I skipped. This result, this optimization result, is true only if this condition holds. So this sum of square root of the JCJ is bounded. Otherwise, I don't know, run the calculation, I don't know what happens. I don't know if the solution doesn't exist, or surely it cannot be that one. We will have different approach. Okay, so let's assume that as we did yesterday, so we use geometric sequences of refinements with a certain factor delta, that the V tilde, these second moments, non-centered second moments, decay as some power beta of the mesh size, hj to the beta, which means delta to the j beta, and that the cost increases at some negative power of hj, so hj to the minus d gamma, which will be delta to the minus j d gamma, proportional to. And then if we use this optimal probability, so this will hold only when this infinite series is bounded, which means the sum of j of delta j beta minus d gamma over 2. Okay? So from here you see that this infinite series is bounded even only if the beta is larger than d times gamma, which was the best case in the standard multi-level Monte Carlo analysis. Okay? So if we are in this good case, beta larger than d times gamma, these pj's from this optimal formula scale like delta to the j beta plus d gamma over 2. And then we can look at the overall mean square error for a given cost, which is the same as the variance. So again, I used the formula for the variance. We have a typo here. And I have a typo either on this slide or on the other one. I believe there should be a square. Let's see. They put a square here. So if I take this product Cj Pj. Well, it doesn't matter. So I guess there is a square, but it doesn't change the result. So if I take this infinite sum of Cj, Pj.
What was the Cj again, sorry?
Cj is the unit cost to run the simulation on level j, which grows that way. So when I multiply these two, I get again back delta to the j beta minus d gamma over 2. And again, if I am in the good setting beta larger than the gamma, this is a converging series. So I just get something that scales like 1 over k. So the mean square error is proportional to 1 over k. So I can reverse this inequality and say that the cost scales like the mean square error or the tolerance to the minus 2. Okay? Which is the same result as for the multilevel Monte Carlo in the best case. Okay? So somehow this unbiased version performs as good as the multilevel Monte Carlo if you are in the nice setting beta larger than the gamma, and essentially doesn't work if you are not in the good case. Okay? So that depends on which case you are. If you are in the good case, you could use this unbiased version, and it's somehow nice. Okay. So that was, I think it's a nice variant of the multilevel Monte Carlo that could be useful in certain settings. For instance, we have used, so in some stochastic optimization problem, you have, so let's say you want to solve it with stochastic gradient descent. And you know that if you do stochastic gradient descent, you should use unbiased estimators. Otherwise, if you have a biased estimator, the bias should go to 0 in the limit. Okay? But if you have unbiased estimator, you can have an estimator that has large variance, and you just play with reducing learning rate to converge to the optimum. So then, in that context, one could use this estimator here, meaning that at each iteration of my stochastic gradient descent, for instance, maybe I just draw one level and one difference, and I use it as an estimate of the gradient, and then I keep on going with the stochastic gradient descent, and hopefully we'll converge. Yes.
I have a question about the practical realization of the method. So what would happen in an unlikely case that you would need to compute on a very fine level in which you cannot compute? You just leave it out and then have a slightly unbiased estimator, or is there some other trick to play?
And then you have a bias, yes. So
sorry, bias,
The assumption here is that, I mean, if you aim at converging at a true value, at some point you have to use an infinitely refined grid. So, of course, if you are limited by budget constraints, then you have to truncate anyway the series up to the maximum level, and then in practice this will be a biased estimator.
Okay.
So, I agree. If you put a limitation on the resources, you will not have an unbiased, but you could hope that the limitation is not so strict, so certain problems virtually you could refine a lot, but this gives you an indication on how often you should run on a very, very fine grid. So most likely if you target a tolerance that is not too stringent, you will never visit very, very fine grids. But yes, I mean, the cost is only bounded in expected values. It means for some cases you might have a way much larger than the expected costs, or maybe too large. Okay. Other extension of the multi-level Monte Carlo, something we proposed a few years back, and we named multi-index Monte Carlo. The point is, so this whole construction of the multi-level Monte Carlo uses these differences of evaluations on two consecutive grids. So we assume that we have some discretization parameter, and we can build a hierarchy with an index L and then we can construct differences onto consecutive levels. So what happens if I have multiple discretization parameters? For instance, I have this mesh size, space mesh size, I have the delta t, or if I can do some particle system, particle approximations, and have the number of particles in my kinetic model, whatever. If I have to solve an unbounded domain, I will have to truncate the domain at some point. So I might have a truncation of the domain as a discretization parameter as well. So you could imagine of having many possible discretization parameters. So if you want to follow the multi-level strategy, you have to link all of them. So I can say in the coarse level, I use this mesh size, this delta t, this number of particles, and this truncation. Then I go to the next level, I use a finer delta h, a finer delta t, a little bit larger domain, a little bit larger number of particles, and you have to find a good way of constructing a hierarchy over these particles. And then the idea is, okay, can we refine them independently? Question mark. Okay, we play with different L. So L becomes a multi-index. So it's not one number, but is a vector of few numbers, which defines the level of refinement for each of the discretization parameters. Okay, so here I denote all of them with H, but they could have many different meanings. So H1 is, for instance, the spatial one, H2 is maybe the delta t, H3 is the truncation of the domain, and so on. Okay? And now for each of those, individually, I introduce a hierarchy, so a sequence of refinements. Okay? And then what simulation exactly I run will be identified by this multi-index L1 up to LD, which says, okay, on X I should use this level of refinement, on T I should use this other level of refinement, and so forth. Okay? And then for every multi-index L, it will correspond a certain solution with for my discretized problem. So suppose you have two parameters, just because it's easier to plot. So L1 and L2, and then those are the levels of refinements in L2, those are the level of refinements in L1, and then if I pick any point here on this lattice, it will correspond to some numerical solution. It should be clear that the farther I go in this direction, the more refined solution I have, so eventually I go on that diagonal, hopefully I will converge to the true solution. Okay? So if I want to converge, I have to let both L1 and L2 go to infinity. Okay? So now we are in 2D or in D dimensions, so how do I take differences? So I do compare models. I have different ways of comparing models. So I could compare, for instance, this one with this one. So I could only look at refinements along the diagonal. That would be the multi-level strategy where you link the refinements over the two parameters. Okay? But I could also look at other differences. I could look at this versus this versus this one. So I only refine in space, I only refine in time, or I refine in both. So I could consider other differences as well. So could I profit for this one and this one in the overall construction? Would that bring something more than just looking at the differences along this layer? So here again, if you think of having two discretization parameters, so this is a refinement grid, this is a coarser grid where I coarsen in both, but I could decide to coarsen only in one, so compare those two solutions, or coarsen only in the other direction and compare those two solutions. Okay? So for each, so if I have the multi-index L, let's say this one, okay? I could take this difference here, so I call it delta J QL is the difference with respect to the jth parameter. So I compare the solution QL with the solution QL minus EJ, where I coarsen in the J discretization parameter. So that would be either this one or this one. And of course, if I am on the boundary, there is no difference, so it's just the value on the boundary. So whenever Lj is equal to 0, it's just the value. But again, I could write it as a difference with the usual notation that if this is -1, then by default is 0. Okay. Okay, so that's a single difference. And then what I can do is take the tensor product of those differences. The tensorized difference, I take difference of differences. So this delta, this tensor product, will be this difference minus this difference. It's a double difference. It's at the same time a difference in these parameters and in this parameter. Okay, so again, in 2 dimensions, this double difference, so this delta QL, if L is just L1 and 2, with 2 parameters, will correspond to taking QL1 and 2, that's the most refined way. Then I coarsen, let's say, in the first, so that would be QL1 minus 1 L2. And then this difference, now I take the difference of this with respect to the L2. So I subtract the same quantity, but evaluated for L2 minus 1. So this would be QL1 L2 minus 1 minus Q L1 minus 1 L2 minus 1. Okay? So it's a double difference. So now it involves 4 terms. This one has a sign plus, this one has a sign minus, this one has a sign minus, and this one has a sign plus. It's plus, minus, minus, plus. Okay? So this was in 2D. If I go to 3D, how many terms, how many elements will I have in this double difference? So if I have an extra parameter, I will have to take now a further difference. So I will have to take the difference of all these with L3 minus the same quantity in L3 minus 1. Okay. So this grows like 2 to the d. So if I expand this double difference in dimension d, I get all possible combinations of QL minus a vector j that can take value 0, 1. Okay, and I get all 2 to the d terms in this sum with alternating signs depending on if I take a number, even number of coarsening or an odd number of coarsening. So this minus 1 to the length of j takes track of the order of the coarsening. Okay, so now. How do I generalize the telescopic sum that was at the origin of the multilevel Monte Carlo? Well, this telescopic sum does have a multidimensional extension, generalization, using these multiple differences. So if I take, again, some target, let's say that this is the final discretization I'm happy with, satisfies the tolerance on the bias, with parameters capital L1 to capital LD. So let's say I want to compute this expectation here. Well, it's a little exercise to show that this is exactly equal to the sum over all multi-indices smaller or equal than L. So this is an entry-wise comparison. So little l is smaller or equal than capital L. There is at least one entry that is smaller than the corresponding one of this mixed differences at level L. Okay, you can show it just by recursion because I mean, if you sum, this is a multiple sum of all the entries of the L. If you sum the last entry first, that's a telescopic sum, so you only have the last term, then you go recursively and you get this identity. Okay. So, okay, now we have a generalization of the telescopic sum formula. So if we want to build an estimator, now a possible estimator is to say, okay, let's use an independent Monte Carlo for each one of these deltas. Okay, we have many more terms to compute, but maybe give something. Okay, so first version is to say, okay, I sum over all those terms, and I use a simple average for estimating each one of those deltas. Okay, again, this is a graphical picture, so I'm targeting this level of refinement, but now I'm summing over all these points in this lattice. For each one of those, I have to compute this multi-difference, so all these terms here and recombine. Okay, so if you do this, you don't gain that much. You may gain a little bit. I will show the results, but it's not really what makes the difference. What makes the difference is to realize that when you sum all those delta contributions, all of them up to this point here, you do expect some decay of these deltas, because you are refining some parameters. So let's say if I refine one parameter, I may expect that this difference, when I refine in this direction, decays at a certain rate with respect to this discretization parameter. When I refine in that, it should decay at some other rate. But when I refine in both, what do I expect this delta, double delta to decay? Well, it's a double difference. So think it's a stupid example where, let's say, you just want to approximate a function. Let's say I have some function of x1, x2, and I consider some double difference taking some increment. So I compute f x1 plus some h1 x2 minus f, sorry, plus h2, so that's the increment point, minus f x1 plus h1 x2 minus f x1 x2 plus h plus h2 plus f x1 x2. Okay, so that's a double difference. So this difference here is a difference in the h2 parameter. So this should be proportional to h2 times some derivative in the x2 variable of the function f. Okay. This one, if I group this term, is also a difference, but this is evaluated in x1 plus h x2, h1 x2. Okay. This one is also a single difference in h2, so again it's the case like h2 set the derivative in x2, f evaluated in x1, x2, and now I have a difference. So now I'm taking the difference of those two objects. So in this case, like h1, h2, second derivative x1, x2, f in x1, x2. There is of course plus everywhere. The even order is this one. Okay. So what does this stupid example shows is that if you take this double difference just on the valuation of the function, so the single difference scales like h 2 or H1, depending on how you order the difference, which difference you take. But the double difference case like H1 times H2. So it's a product of the two, right? Okay, it's not the sum. It means that the diagonal terms is when I move on the diagonal, those deltas decay very, very fast because it's a product of two rates. So this term here should be super small compared to this one or this one. Okay? Now there is a catch here. It's a little catch. What do I need to assume here to get this rate? Well, I just need to assume that the function is differentiable in x2, okay? Or in h1 if I do the other difference. What do I need to assume here? Well, I need to assume that the function is twice differentiable. Twice in the sense that it has this mixed derivative x1, x2. Okay? So I'm requiring more to get this product rate. I'm requiring more regularity on the function than to get a simple rate. Okay? This is something you should not forget. But if you do have this mixed regularity, okay, then it's way much more difficult to prove it for, let's say, a PDE when you refine or when you take these double differences, refining it in the different directions. But the intuition is this one. Okay? So, conclusion is that if you have this sort of mixed regularity again means that somehow if I do a difference in one parameter and I get a rate, this doesn't impact the regularity on the other parameter. So I can then take another difference in the other parameter and get the other rate. Okay, that's why it's called mixed regularity. So, of course, if my function is only C1, it will not work. Once I've taken one derivative, I have no regularity left. Okay. Okay. Good. So the whole point here was that when I sum all those deltas, they are not all of the same size, and they should, if I have this mixed regularity, I should expect this term here to be way much smaller than this one and this one. That means that maybe I can throw it away. And maybe I can throw it away all the upper part of this triangle, because all those terms should more or less have equal size. Well, this is in case you do geometric refinement. If I do geometric refinement, so H1, I can now say that my H1 was some H0 to some delta 1 to some power L1, and the H2 was also some H0 delta 2 to the power L2. Okay. If I get the product of the two, I will have delta delta 1 L1, delta 2 L2, which I can write as, let's say, exponential of L1 logarithm delta 1 plus L2 logarithm of delta 2. So this is a so now you say that all the terms that are on this line that have the same linear combination between L1 and 2 with these weights, they have more or less the same error contribution. So all the terms on these lines that correspond to these linear combinations, they have more or less the same size. So if I target a certain accuracy, I should add all those lines up to this accuracy, and then there is no much point in going further than that. Okay? So that's what is called the sparsification idea. And this will be actually much more effective than that one, under the assumption that you have this mixed type regularity. So that will be the final estimator. And actually you can, so this was in this ideal setting, and I can throw away all those terms. Of course, if you have a good bound on this derivative of these mixed differences, essentially you can go and check what terms you want to retain and what terms you want to throw out, and we'll do it in the next slide. So this, then the idea is to define an index set, so you define which deltas you want to keep in your approximation based on this type of analysis, and then you form this multi-index estimator. Okay? All right, a little bit of analysis. So, what's the bias of this estimator? Well, we'll just take an expectation here. This Monte Carlo estimator is unbiased. So my bias will be the sum over all the indices in the index set of this expected value of the delta. Okay. Knowing that, again, if my approximation is converging, so if I let this multi-index L go to infinity, I should recover the Q exactly. So again, I do have this sort of hierarchical expansion of the exact expectation of Q. Like in the unbiased one, I use this infinite series. So when the bias then would be the difference between this and this, which is essentially the sum over the complement. So if I want to characterize the bias, I have to understand what are the sum of these deltas over all the complements, so all the terms that I've thrown away. Okay? So the bias will be the norm of the sum of these expected deltas on the complement. Now, of course, it's very difficult to deal with this, so let's play sloppy and use a triangular inequality. So if I have a good estimate of the size of each one of those terms in norm, I can upper bound the bias by the sum of those error indicators in L over the complement. Okay? What's the variance? Well, it works pretty much like in Monte Carlo, Multilevel Monte Carlo. So the variance is the sum of independent Monte Carlo estimator. Each one is a Monte Carlo estimator, so it will have a variance over sample size. So the variance of this multi-index is here. So there's another typo. So that's the variance of the estimator, not just the delta. So the variance of the estimator will be the sum over all the levels that I have retained, or all the multi-index that I have retained, of the variance of the corresponding Monte Carlo estimator, which is the variance, the L of the quantity itself, so it's the variance of this delta, divided by the sample size that I use on that level. Okay? And then you can work out, once again, the optimization. So now what do we need to optimize? We need to optimize two things: the choice of the index set, which delta do we retain, and the sample size to use on each index. Okay? So again, we try to minimize the overall cost, which will be the sum of the unit cost to calculate each one of those deltas times the sample size ML. Subject to variance being smaller than tau square. Okay? Sorry, this is just for the variance part. And then for the bias part, the bias will dictate the index set. So you have to take the index set so that the bias is also smaller than tau square. This optimization looks very much like the one in Multilevel Monte Carlo. Okay, I have just a more general index set, but it works exactly the same, so you get exactly the same formula. So the sample size on each level, multi-index, should scale like this square root of VL over CL, suitability in this case. And then you plug this into the cost. So the cost of the MIMC estimator is tau to the minus 2 times this sum of the square root of VL CL. Okay? Plus this round of the ceiling part, which we forget. Okay. What about the choice of the index set? So you also can phrase an optimization problem there. So you want to minimize. So now we have an expression for the optimal cost. So now I want to decide the value. You want to kill the bias, so you want to decide on the index set. So we want to minimize the cost. We find the best index set that minimizes the cost, given that the total error or total upper bound of the error is smaller or equal than the tolerance. Okay? So now I fix the bias level and I find I that minimizes the cost, having chosen already the optimal sample sizes on each level. So minimizing this cost is equivalent to minimizing the square root of this cost. So throw away the square, just to simplify the calculations. And then this is a nice optimization problem. This actually can be recast into a knapsack optimization problem. So you leave for a trip, you need to take a backpack, and you have to pack things in the backpack, and you have to choose each item has a volume and a value, and you have to decide what's the optimal strategy, what you want to put in the backpack. The optimization, the exact one is difficult, but if you relax a little bit, it has a nice, easy solution. So what you should look at is the ratio between the error, the L, and the cost, the unit cost. I call this the profit. And then you should list all the multi-indices by profit, and you take the most profitable one. And that's the optimal solution of this problem. So it means that, let's say I pick some threshold nu. For this threshold, the optimal index set that you should choose is the collection of all multi-indices for which this profit is larger than nu. Okay? And nu, you should find it to meet the tolerance requirement. So again, somehow what you end up with is that lines of this type, and you should chop at the right point. Okay, again over time. Okay, this is a proof of the so the statement is that these sets are optimal in the sense that any other set, so for a given nu, any other set that has a smaller cost will surely lead to a larger error. Okay, so you cannot find another set that has a smaller cost and a smaller error. Okay, so in this sense it's optimal, and here you have a simple proof of the optimality. So in this paper here with Buratif, Gioli, and Tempone, back in 2015, we did a complexity analysis, again making assumptions on the decay of these deltas. And we did this, the analysis in this assumption that we have this mixed regularity. So it is indeed true that these deltas decay as the product of the rates in each individual variable, which is not granted, not always true. So there's a big question mark that one has to verify problem by problem and to understand whether you do or not, or don't have this type of mixed regularity. So assume we do have, so the delta Q in expectation decays as the product of these individual rates, H and J to some alpha J. Again, we use geometric refinement for each of those parameters. The variance decays as well as the product of individual rates with some power beta. And the cost also is the product of rates in the cost. If you do a double refinement in two directions, the cost should increase as the delta 1 times delta 2. Delta 1 over delta 1 times 1 over delta 2. So under these assumptions, you can evaluate what the profit is, and this will scale like this delta j to the lj, the product of delta j to the lj times alpha j plus gamma j minus beta j over 2, so this comes from the denominator. Remember that the profit is E over square root of LC, so E scales like h to the alpha, and the square root of LC scales like h to the beta plus gamma, minus gamma, whatever. So you get this expression for the profit, which now again I throw it to the exponential, so I can write it as the exponential of this weighted sum of the levels, and that's my criterion now to threshold. So the index set is defined by enforcing that this exponent here, so all the multi-indices for which this exponent is larger than some fixed value, which gives this type of simplices to select the indices. What can we show in terms of complexity? We can show essentially this result. There is one optimal case. So remember that in the multi-level, standard multi-level, the good case was beta larger than d times gamma. And there is this d there because of this cost in d dimensions. Now suppose that they're in d dimensions, but you do this different refinement in each direction. So now you recover the optimal complexity told to minus 2 under a way much weaker condition, which is beta j larger than gamma j for every j. So individually, for each refinement, you have to make sure that the variance decreases faster than the increase in the cost. But not all together. So if you do them all together, you just have one beta, but here you have this factor d. So at some point, this will not be satisfied, but the individual one might still be satisfied even if you go in dimensions. So if you have 3, 4, 5 parameters, as long as each one of those satisfies this condition, you get this optimal. Okay, I think I stopped. So this is a comparison between the standard Monte Carlo, the multi-level Monte Carlo, and the multi-index Monte Carlo for some different cases. So here is the case where, where the strong rate is smaller than the weak rate. Maybe I show the simplified version where the strong rate is equal to twice the weak rate. But the main difference is that you have very similar cases. It gets a bit messy, get complicated. The main difference is that you remove this d here in the classification. So you have many more cases where you fall into this optimal told to the minus 2. And if you don't, you essentially get this complexity told to the gamma over alpha, where here I'm showing all the alpha or the beta are equal. So this told to the minus gamma over alpha now, in the Monte Carlo, the cost is d times gamma over alpha, because you're solving a d-dimensional, you have refined it in all directions. Here you have a cost that is told to the minus gamma over alpha without the d, so you only see the complexity of a one-dimensional problem when you only refine in one direction. So it looks like the cost of the mimic is essentially the one of solving, in this case, a one-dimensional problem. By one-dimensional, I mean only looking at one type of refinement. Okay, the complexity of refining only one of the parameters, the worst one. Okay, let's stop here. And back to the multifidelity of this.